Good evening. Obviously, we're going to bring you the latest news from the Phoenix probe on Mars. But first of all, something quite different. The biggest bangs of the universe, gamma-ray bursts. With me, Dr. Julian Osborne, and of course, Dr. Chris Linton. Welcome, gentlemen. May I come first to you, Julian? Gamma-ray bursts, what exactly are they?
Well, as you say, they are the biggest bangs in the universe. They're the most extraordinary explosions. We think they're due to the deaths of generally massive stars, and we can see them probably across the entire universe.
But we can't see them with the naked eye, can we, Chris?
No, though they're very, very powerful explosions. Most of the energy is concentrated at the very energetic end of the electromagnetic spectrum. That's why they're called gamma-ray bursts. Gamma rays are even more energetic than X-rays. There's very little light in the optical that we can see, but there was a burst just a few weeks ago, in fact, Julian, that should have been seen with the naked eye. Yes,
magnitude 5.3, so if you were looking in the right direction at the right time and you had a dark sky, you might have seen it.
How long did it last?
Well, less than a minute, so you'd have to have been pretty lucky, frankly.
You will indeed.
But it was an extraordinary event. The previous most brightest gamma-ray burst in the optical was about magnitude 9, so this was very much brighter.
How far away is the most distant gamma-ray burst ever recorded?
Well, funnily enough, we detected the most distant one just a few weeks ago. It was at redshift 6.7. Which means that the universe at that time was just 6% of its current age. And in fact, this is one of the very few most distant objects known in the universe.
How bright did it look?
This was not a very bright object, but of course, to instruments around Earth, it must have been intrinsically fantastically bright.
What kind of stars are liable to produce gamma-ray bursts? Can you elaborate on that a bit, Chris?
Sure, well this is in some sense a fairly natural process, although it's violent. It's what happens to all massive stars, those much bigger than the Sun. What happens is they run out of fuel at the centre, there's nothing to support them, and so they implode. Most of the outer layers get thrown off in what we call a supernova. We see the emission from the radioactive material produced during that explosion, but the core collapses and produces either a black hole or something called a neutron star, a dense body, extremely dense, which we sometimes see as a pulsar if we have radio emission from the poles. And actually these neutron stars have a role to play in some of the more unusual gamma-ray bursts.
Yes, in fact there are two types of gamma-ray bursts, the so-called long ones, which we think are associated with black hole formation as the massive star collapses. The long gamma-ray bursts may be a minute or so long. A short gamma-ray burst is one which is less than 2 seconds long and might even only be 10 milliseconds long. We have two neutron stars which were probably a binary star in the previous stage of their evolution. They're going round each other in orbit. That orbit shrinks and they spiral in, getting faster and faster, and eventually they hit each other and cause this most tremendous explosion.
Well, these things are not all that common, are they? But I believe 5 did occur on one special occasion a little while ago.
Yes, an extraordinary 24 hours. This was in the 19th of March of this year, 2008. Coincidentally, the day that the famous Arthur C. Clarke died, we had 5 gamma-ray bursts in one period of 24 hours, an extraordinary event for us, because ordinarily we are seeing just one every 3 or 4 days.
Knowing Arthur, he probably planned it.
Well, it was truly a remarkable thing.
They do leave traces, don't they?
Afterglow. We think it's the collision of the ejected material with the gas which was surrounding the star. The initial burst is coming from quite close to the star, but then later, as this material is rushing out at these hypervelocity speeds, it ploughs into the surrounding medium of the galaxy that the star is in.
Are there any nearby candidates? I mean, Oh, Eta Carinae, for example?
Eta Carinae is a reasonable candidate. It's not a binary, so we don't have that, but it is a massive star. It's more than 100 solar masses, and it's a weird-looking thing. I mean, you can see these enormous lobes coming off it, which is clearly some sort of extended envelope, and I'm sure there's mass loss going on. So I think this is a star that is losing its outer layers, its hydrogen and helium. So I think I can confidently predict that Eta Carinae might well produce a gamma ray burst. The thing is, we'll have to wait a few billion years.
Another my first view of Eta Carinae through a telescope. It doesn't look like an ordinary star. It's a kind of red blob.
Yes.
And about 1840, it shone as the brightest star in the entire sky apart from Sirius.
In fact, some gamma ray bursts, or at least one gamma ray burst, is thought to have emitted a shell of gas a few years before it exploded.
So maybe that's what was going on in 80. We're now rampantly speculating. The hard thing is putting your finger on a star and saying, yes, definitely this one, but that's the best candidate.
But of course, space research comes in here. We have the Swift satellite.
Swift is amazing. You must talk about Swift.
Well,
this is your project.
So Swift is indeed pretty amazing, and it's amazing for two different reasons. One is it's focused on the subject of gamma ray bursts, and so it has a big gamma ray detector which looks at a large fraction of the sky waiting for gamma ray bursts, and when it detects one, it's able to react very quickly, and within a minute it will point its X-ray telescope and its optical telescope, which are co-aligned, onto this exploding star.
Is that why it's called Swift?
It is indeed why it's called Swift. The project has a kind of motto, catching gamma ray bursts on the fly, which is what Swifts do. They catch insects on the fly.
And the remarkable thing about this is it solves the big problem for gamma ray burst astronomers, in that in the old days when these things were being studied more than a decade ago, all you'd know is that a gamma ray burst had gone off somewhere in a 2-degree patch of sky. Now, the full moon's half a degree across, so that's 4 full moons. And imagine saying somewhere in there is something that's caused this burst. It's hopeless. Whereas with Swift, because you go quickly to the X-ray and to the UV and the optical, you get down to it's this galaxy, and then you can trace it with big telescopes.
Yes, exactly.
And how do you measure their distances?
Through the redshift of the spectral lines. So essentially what we do is, with Swift, we measure the position of the burst, and that enables people on the larger ground-based telescopes to use their spectrographs to take spectrum, and then by identifying the emission lines in the spectrum, they can say what the redshift is, and that's how you measure the distance.
Chris, what about Fermi?
Oh, well, this is the new American satellite, and it's doing something interesting. It's not specifically aimed at gamma ray bursts, but it's looking at a region of the spectrum we've never explored before. It's looking at a really high energy gamma rays, even way beyond what Swift, for example, is looking at, and they turn out to be important for understanding gamma ray bursts.
Well, they do. We hope that Swift and Fermi will simultaneously detect some gamma ray bursts, and it's very important to understand the total energy output of the gamma ray burst, because that tells us how much mass is involved. And by looking in this very high energy part of the spectrum, we can measure the total energy output.
I want to ask Julie a question because I want to use gamma ray bursts, so I want to see if this is possible. What we love in astronomy is things that are what we call standard candles, things that are always the same brightness, or we can work out their brightness, because then when we see them in the distant universe, we can use them to measure the expansion of the universe. Now, gamma ray bursts would be perfect. They're bright. We can see them from 13 billion years ago. What hope do I have of getting an understanding of gamma ray bursts good enough that we'd know what brightness they are?
This is a fantastically controversial subject.
Yes, that's why I'm asking you. We've got an expert sitting.
Yes, well, so the question is, are they standardizable, really? You know, we use the supernova 1A in the near universe for measuring the expansion of the universe. And of course, gamma ray bursts occur, you know, up to at least 6% of the age of the universe. They hold great promise. People are working very hard to understand the relationships between the energy they emit and their spectra, to try to work out if that relationship really stands up. There are plenty of people who think it does. There are plenty of people who think it doesn't.
Well, I wonder. Certainly we're going to learn a lot more in the foreseeable future. Julian, Chris, thank you very much.